Hi, so today we're starting a new unit. This unit is on thermodynamics, and there's a lot to this, most of which, or the most difficult part, comes way at the end, Unit 9, which is, I think, like advanced applications of thermodynamics or something silly like that. This is sort of if we had 3 more weeks last year, we would have gone into about 50% of this last year, but a lot of it is very intuitive. There's some formulas, but the formulas are way easier than they were in kinetics. There's no logs. It's just numbers, plug in, add, subtract, multiply, divide. Pretty straightforward. As we go through all of the different topics, most of them are in chapter 5. So we're going to basically do chapter 5 from beginning to end. So if you want to read the textbook, that's where you would begin. There's a couple topics that are hidden in chapter 8 and chapter 11, and we'll do those at the end. This is about thermodynamics. So therm means heat. So we're going to talk about endothermic and exothermic reactions or processes, and why some reactions are exothermic, some reactions are endothermic. The energy diagrams, that's just pictures of them. Heat transfer and thermal equilibrium, that's the idea that if you put, a hot piece of metal into a cold glass of water, the hot metal will transfer its energy to the cold water till they are the same temperature. Something that you instinctually had figured out. Now we're just going to put some math to it. Key capacity in calorimetry is how do we measure that? So we know reactions are exothermic or endothermic, and last year we did problems where delta H, and we did like stoichiometry with it. So this is, where does that delta H come from? Like, how did we figure that out? And that's going to be one of the major questions in this unit is, where did delta H come from? Because many questions are going to be, what is delta H of this reaction? And there's 3 or 4 different ways to find that out. So we're going to learn each one. And then what it will be difficult on the test will be, given the data in the problem, which one of those methods do you use? This is the second way to find delta H, with the enthalpy of formation. And another way to figure it out, something called Hess's law. So the beginning of this unit is just going to be really getting some basic vocabulary down around what is energy, since thermodynamics is all about energy. So energy is defined as the capacity to do work or transfer heat. And we often think of energy is the same as temperature. Energy is analogous to temperature. And it is, but there's a whole nother aspect of energy, which is this work piece to it. And I will say that work piece is where, chemistry and physics crosses over many, many, many times. And this is an instance where the work piece kind of veers off into physics, and we sort of just focus on the heat piece of it. But as you can see, like this picture over here, if you have a chemical reaction that goes on inside this cylinder, right? If that chemical reaction produces gas and that gas expands, it will have done work, because work is the energy used to cause an object to move against a force. So pushing that cylinder up, that's moving against the force of gravity. And so there's a chemical reaction that has done some work. Most of the time, most chemical reactions that we're going to look at do no work. But chemical reactions doing work is the basis for just about every thing around us, cars and electricity. So it is really important. So heat. So like we said, energy is this heat and work thing. So heat is obviously something that's really important. The technical definition of heat, which last year we just sort of heat, energy, temperature, kind of the same thing. And now it's we really do need to know the difference between all 3 of those. So heat is sort of a specific form of energy used to cause the temperature of an object to change. And we know the temperature of an object is related to the kinetic energy of the molecules, and the kinetic energy of the molecules is related to the velocity of the molecules. So this picture here probably is yep, I know that picture. It's showing that, hot air, or the molecules that are hotter, are moving faster than molecules that are colder. Pretty straightforward. And then we have kinetic energy, which of course is related to heat because it's the energy of motion. And if those particles are in motion, they're displaying kinetic energy. And again, here we have one of my favorite graphs, a Maxwell-Boltzmann distribution, as it's sometimes called, and just reminding us that at any time you have sort of a system at any temperature, some molecules have really low kinetic energy, some molecules have really high kinetic energy. And what changes with temperature is the fraction, you can see it over here in red, the fraction of molecules with higher kinetic energy or more kinetic energy. This is, why when water spills on the ground, why does it eventually all evaporate, even though it never gets to the boiling point of water? Like, what's going on there? And it's because at some point, all of those molecules will have enough energy to overcome the hydrogen bonding that's holding it together as a liquid and become a gas. And then potential energy. So when you start talking about potential energy in middle school, the example that they always give is, the roller coaster at the top of the hill, or holding a ball up high, energy due to position, which is not wrong. It is energy due to position. And we call this like stored energy. When we talk about this in chemistry, though, it's not about being at, the top of a hill. There's no hill here. It's really all about the idea of this position, and we're going to learn it's sort of chemical bonds. That's what this electrostatic potential energy, right? Electrostatic, think of like electrons. The potential energy due to the position of two charged particles relative to each other. That's basically bonds. That's what this is coming down to. The potential energy stored within the bonds. And that really is, that's what we are going to describe as chemical energy. So this is, of course, we're talking about energy, we're talking about electrostatic potential energy, just as a reminder that this is all going to be about Coulombs Law, which, everything in chemistry, most things, can be boiled down to Coulombs Law. This is the formula for it. You'd never need to plug in numbers for this formula, but you do need to know the meaning of it. And basically, you must remember this from first year chemistry, that what do these Q's stand for? They stand for the charge. So the greater charge equals more force. Most of the time we're talking about opposites attracting, so we're talking about a force of attraction, but it could also be force of repulsion. And then the greater distance, you see how that's in the denominator, so the larger the distance, the less force that there is. Less force of attraction. I always think of these as like magnets. If you have really strong magnets, the force of attraction is strong. If the magnets are far apart, there's not as much attraction. And like I said, this is what really, when we're talking about potential energy, that's what we mean by chemical energy. When you say like a Snickers bar has a lot of energy, it's going to give me energy. What that means is that it contains a lot of calories. That's one of the units that we use to measure energy. And that means that the bonds that are in the molecules inside that Snickers bar have a lot of potential energy. And if we can harness that potential energy and convert it into other types of energy, we could use that energy. And that's what our body does, is it takes the potential energy stored within mostly the sugars in a Snickers bar and converts that into different types of chemical energy, then parts of it are thermal energy, and then eventually kinetic energy. That's how we move, right? So chemical energy is this is like the chemical version of potential energy, and thermal energy is the chemical version of kinetic energy. So if you think about like when you learned potential and kinetic in middle school, and you learned about like the roller coaster or whatever, that works perfectly well for physics, but it really doesn't describe how those apply to chemistry. And so if you think of it in terms of potential is chemical and kinetic is thermal energy, it makes a little bit more sense. So here's, kind of sort of wrapping this whole introductory piece up. We get one of our biggies, energy is never created nor destroyed, the conservation of energy. Also, we have the conservation of mass, and then physics tells us that mass and energy are really two different sides of the same coin. But energy is never created nor destroyed. It's simply converted from one form to another. And this is the basic tenet of how literally the entire world works. Everything that you look around you is just energy being transformed from one form to another form to another form, right? When you're driving in your car, that's, you're burning fuel. So you're taking the chemical energy that's in the, octane and all the other chemicals that are in gasoline and converting it through combustion into thermal energy and into work, because it's pushing those pistons away. Think of in a coal-fired power plant, you're taking the chemical energy that's stored in the coal and converting it to thermal energy, which then gets converted to mechanical energy, moving a turbine, moving magnets against copper coils, and that creates electrical energy. And then go back further. Well, how did the coal get the energy? Well, that was electromagnetic radiation from the sun being converted into chemical energy by plants through photosynthesis, right? Where did that energy ultimately come from? And we know that's the nuclear fusion that's going on in the sun, right? My little solar bobbleheads in the back of the classroom, right? That's the electromagnetic radiation from the sun through a solar cell being directly converted to electrical energy. And that's a really unique and really promising form of converting solar energy into electrical energy without having to go through all of these steps. The process here is really converting solar energy into electrical energy, but there's so many different conversions along the way that aren't 100% efficient. We lose a lot of that energy in the form of heat, mostly in the form of heat. So, solar cells, photovoltaic cells, are really promising when we're thinking about how this is moving forward. And the last little bit of 5.1 here, units of energy. So we've used these before. Joules is the unit of energy that we are going to use. It is a capital J, not a lowercase j. We will often talk in terms of kilojoules. That is a lowercase k, capital J, again, kilojoules. You might see calories. Calories is it's like the feet to our meters. It is not an SI system, but it's used a lot in biology, and it's even used a lot in environmental science. But we are going to be using joules exclusively. The system versus the surroundings. This is the idea, and it's kind of weird that we even need to really talk about this, but the system is what we are studying, and the surroundings is everything else. If you look at this picture right here, this would be inside this cylinder are the hydrogen and oxygen molecules. And then they're in this piston. Matter can't leave because it's sealed. Energy can leave as heat or done by work. In this scenario, H2 plus O2 will combine to form H2O. That's not a balanced chemical equation. That's just the combustion reaction. But so this would be the system. And this is an explosion. So this would lose heat and lose energy. But then what that means is that the surroundings, literally everything else, would need to then gain that energy, because as we said, the conservation of energy is never created nor destroyed. So if the system loses that energy, the surroundings must gain that energy, and vice versa. And this is just the idea that, yes, we can experience the transfer of energy as either heat or work, and depending upon the system, we get one or the other or a mixture of them both. So that's sort of a lot of terminology, a lot of definitions, just making sure that we're all starting with the same basic set of vocabulary.